Welcome to our second lesson in our series on the atmosphere. In our previous lesson, we explored the Earth's atmosphere in its current form and described it with relation to its chemical composition. We also described the way temperatures change with altitude in the atmosphere. But here's an interesting question for you. Do you think that the Earth's atmosphere has always looked the way that it does today? There are many different opinions about how our world came into existence. Some of these are part of indigenous knowledge systems and oral traditions. Others are part of mythological and religious belief systems. No one can say with certainty exactly how our planet and life as we know it came to be. But as science is our focus, we'll be looking at the most accepted scientific theory about the origins of Earth, and specifically Earth's atmosphere, in today's lesson. By the end of this lesson, you should be able to identify the 3 stages of the atmosphere's development and evaluate the viewpoint of different value systems on the origins of the Earth. To better understand what makes the conditions on Earth unique, let's take a look at the conditions on 2 of our neighboring planets. Venus's surface temperature is 450 degrees Celsius. Here we would sizzle and fry, while Mars has a surface temperature of minus 53 degrees Celsius. The blanket of gases around Venus is much too dense, and that around Mars is too thin. With an average surface temperature of 15 degrees Celsius, Earth is just right. The most ideal atmosphere to support carbon-based life forms like us formed around Earth. But how did this come about? Join me as we travel back in time billions of years ago to the origins of Earth. Scientists believe that the Sun and the rest of our solar system started to develop about 4,500 million years ago inside a huge cloud of gas and dust called a nebula. The theory is that over many years, the materials inside a nebula slowly pull together into blobs. The largest blob that forms in the center of the nebula eventually heat up and becomes a huge star or sun. The smaller blobs within the nebula orbit around the sun, cool down, and contract to form planets. It's now thought that our atmosphere was being formed as the Earth was developing. The Earth's first atmosphere, formed as the gases associated with the nebula generating the planet, were trapped inside the Earth's gravitational field. These gases were mainly hydrogen and helium. You'll remember that today, most of our atmosphere is made up of nitrogen and oxygen. Clearly, our first atmosphere's chemical composition is completely different from today's atmosphere. So, what happened? Well, helium and hydrogen gas consist of very small atoms. These gases are light. Because of the heat coming from the still hot and molten Earth as well as the Sun, they would easily have been able to escape the force of gravity of the Earth. Essentially, the Earth's first atmosphere leaked away into space. About 3.5 billion years ago, Earth cooled down enough to start forming a very thin crust. As the development of the Earth progressed, so did the development of a new second atmosphere. Imagine the Earth as an unstable place, a hot, stark landscape of volcanic eruptions. These volcanoes shot out many new gases into the atmosphere. H2O, which is water vapor or steam, CO2, which is carbon dioxide, SO2, which is sulfur dioxide, CO, which is carbon monoxide, S2, which is diatomic sulfur, N2, which is nitrogen, H2, which is hydrogen, and methane. This process is called volcanic outgassing. There are a couple of important things to note about the second atmosphere. Firstly, the atmosphere was approximately 100 times denser than the current atmosphere. And secondly, there was almost no free oxygen in the atmosphere at the time. The most abundant gas in the second atmosphere was carbon dioxide. Interestingly, the general belief is that the greenhouse effect caused by high levels of carbon dioxide kept the Earth from freezing during this stage of its development. We'll look into how this greenhouse effect works later in the series. But volcanic eruptions were not the only contributing factor to the second atmosphere. Extraterrestrial bodies were also crashing into the Earth, causing explosions and contributing to the outgassing process. In addition to the impact of these huge rock bodies from space, it is thought that ice comets crashed into Earth. The comets were the size of small houses and introduced additional water vapor into the atmosphere as they constantly bombarded the Earth. As the Earth cooled, the water vapor from the volcanoes and the comets condensed to form ancient oceans and lakes. Until this point in its development, Earth's atmosphere and the atmospheres of its two neighboring planets, Mars and Venus, look very much the same. So why does Earth's atmosphere look so different today? Well, scientists credit it to what is called the Goldilocks phenomenon, something I must admit that is rather unscientific. Perhaps you know the fairy tale in which Goldilocks found the porridge that was just right. Well, it seems that the Earth's distance from the Sun and its size is somehow just right to support the existence of liquid water on its surface. In other words, Mars is too cold and Venus is too hot, but Earth is just right. It is this accumulation of water in all three of its phases that made the Earth's atmosphere evolve very differently from the atmospheres of Mars and Venus. Let's take a look at a few chemical processes that took place to create Earth's modern or third atmosphere. Carbon dioxide, which is a soluble gas, almost immediately started to dissolve into ancient oceans. Here it reacted with minerals to form carbonate rocks. This meant that the carbon dioxide was lost from the atmosphere and trapped in the Earth's crust. Another early remover of carbon dioxide from the atmosphere was chemical weathering. Chemical weathering is an interaction between the lithosphere and the atmosphere. In this process, rocks of the lithosphere are decomposed by chemicals in the atmosphere. The minerals that are released from rock by this process are then available to form new materials like new sedimentary rocks and soil. One example is the way in which limestone and quartz are formed when calcium silicates in rock react with carbon dioxide in the atmosphere. This reaction is represented in the following equation. CaSiO3 plus CO2 react to form CaCO3 plus SiO2. Can you see how this type of chemical weathering effectively removes carbon dioxide from the atmosphere and locks it in the lithosphere? Just reducing the carbon dioxide levels in the atmosphere was not enough to support life. There was one main ingredient missing: oxygen. During the young Earth's evolution, high-energy radiation from the sun split up both carbon dioxide and water vapor molecules in a process called photochemical dissociation. The products of this process then reacted with each other in another chemical process called photolysis. Can you see from the diagram that photolysis also contributed to the decrease in atmospheric carbon dioxide, but more importantly, it increased atmospheric oxygen? The hydrogen atoms formed in these reactions are light. As a result, some of the hydrogen escaped into space, allowing oxygen to build up. This buildup, however, only reached a very low concentration, probably about 1% of the oxygen available today. The bulk of oxygen that is part of today's atmosphere only formed when life began on the planet, mainly through photosynthesis. Let's have a look at the reaction that describes this process. 6CO2 plus 6H2O react to form C6H12O6 plus 6O2. Here, carbon dioxide and water vapor in the presence of light produce sugar and oxygen. How can any living thing appear on Earth and miss the confusion of creating a planet? Scientists still battle with that question. But it is believed that the first living things were bacteria. One type of bacteria, cyanobacteria, also known as blue-green algae, are the earliest photosynthesizing life forms. What is quite astonishing is that some of the oldest fossils in the world that contain traces of cyanobacteria can be found right here in South Africa, in the Barberton mountain lands in Mpumalanga province. Photosynthetic life both reduced carbon dioxide content in the atmosphere and produced oxygen. But the oxygen did not build up in the atmosphere for a very long time, since it was being absorbed by rocks that could be easily oxidized or rusted. As a matter of fact, not until 1 billion years ago did free oxygen stay in the air. I had an opportunity to interview a geologist from the WITS Geosciences department to tell us more about the geological evidence that supports the buildup of oxygen over time. Let's have a look. Good day, Professor McCarthy, and thank you so much for having us. Professor, please tell us about the geological evidence for the buildup of oxygen in the atmosphere.
Right. Yeah, we in South Africa are very fortunate that we've got an extremely long geological history. We've got rocks that go back to as old as 3,600 million years into the past. And there's another thing that's very important that one needs to understand about rocks. You know, rocks are time capsules, because when a rock forms, it traps information about the environment in which it forms. So by studying these rocks, you can actually deduce facts about what the world was like in the past. So these rocks then give us a window into the past. And as far as the oxygen in the atmosphere is concerned, we need to look really at sedimentary rocks. These are rocks that form at surface, on the surface of the earth, usually deposited by various processes. Flowing water is the most common. So by looking at rocks that were deposited, say, in rivers, we can get information about what the atmosphere was like in the past. And one of the very fortunate occurrences in South Africa are our gold deposits, which are in a rock called conglomerate, which is really a river gravel. And these were deposited between 3,000 million years ago and 2,700 million years ago. That's a long time. And the gravel has some interesting minerals in it that give us information on the atmosphere. And here's a sample of one of these conglomerates. This is a piece of the famous Ventersdorp contact reef, which is mined in the Carltonville area for gold. And you'll notice here, these are parts of very large pebbles in this river gravel. And they're made of an inert silicate compound such as you find in rivers today. But here is a completely different kind of pebble. These little pebbles here are made of a mineral called pyrite, which is iron sulfide. Now, these, as you can see, they're rounded. They were deposited by flowing water. It rounded them off and they got deposited here. And amongst this was gold, which is why we extract the gold. These same pebbles today, if you expose this kind of rock to the atmosphere, this is what happens to it. These dark red holes were once that mineral, pyrite, that now, through erosion, has been exposed on surface, and that mineral is completely unstable in our atmosphere today, and it oxidizes to form rust. And the sulfur, it's iron sulfide, the sulfur gets carried away in the water. So we know the fact that these ancient sediments contain pyrite, that there couldn't have been any oxygen in the atmosphere at the time these were deposited. The oxygen would have consumed these, and mineral grains like this could not have formed. We have indications again from rocks and sedimentary rocks, those are the ones that form on the surface of the earth. We can see when oxygen first appeared by looking for the oldest sedimentary rock that contains evidence for iron oxide rather than iron sulfide, such as we find in the old rocks. And here they are. These are the oldest ones in the world. This is also a river gravel. There you can see the pebbles. But now you'll notice that it's all stained red. And this is a rock which is called a sandstone, which is made of sand grains all cemented together. And it was deposited by flowing water in a river, and it's all red. And the reason it's red is because now, when these rocks were forming, iron was oxidizing. So we know there was oxygen in the atmosphere to be able to do that. And these rocks are 2,000 million years old, 2,000 million years old, very old. So somewhere between 2,700 million years ago when these were deposited and 2,000 million years ago when these were deposited, oxygen appeared in the atmosphere for the first time.
So what happened? How did oxygen start building up in the atmosphere?
Well, the story actually is closely linked to life, and in many ways the Earth that we experience today, the surface conditions on Earth are entirely a product, not entirely, but very largely a product of life. And one of the really important things from our perspective is the change of the Earth's atmosphere that life brought about. The first thing that life did was remove carbon dioxide from the atmosphere, and it did that over a period of more than 1,000 million years. It stripped the atmosphere of carbon dioxide. And by 2000, by the time these rocks were being deposited, the atmosphere was basically low in carbon dioxide, but was essentially dominated by nitrogen. So it was essentially a nitrogen atmosphere. So it went from a carbon dioxide atmosphere to a nitrogen atmosphere. Still no oxygen. The oxygen story is very significant because it relates to, again, to life. You know, plants photosynthesize. They take in carbon dioxide and they convert that and release oxygen. The first organisms to do that were, in fact, bacteria. And they called cyanobacteria, and they were doing that. Now, they lived exclusively in the sea. And they basically were taking carbon dioxide dissolved out of seawater and consuming the carbon dioxide, and as a consequence of that, calcium carbonate was being precipitated by sea. Now, these organisms existed as slime layers. They were very slimy organisms. It's just a slime on the ocean floor, really, in shallow water. And so everything was very slimy, and the slime was quite sticky. So the calcium carbonate crystals that formed stuck to the slime. And gradually they would grow through that, and these layers would accumulate. So you see these little bumpy layers here? Those are things called stromatolites, which are formed by these slimy bacteria as they precipitate calcium carbonate and release oxygen into the atmosphere. But the oxygen was not just released free into the atmosphere, because there was another problem, and that was that the sea in those days contained a lot of iron, because of the fact that iron was much more soluble in the what we call the reduced state, iron 2, that's iron 2 oxidation state. And there was a lot of iron dissolved in the seawater. So the oxygen that was released by these bacteria dissolved in the sea, where it came into contact with dissolved iron, and that gave rise to the precipitation of iron oxides. And they formed these rocks which we call banded ironstone. And they formed on a massive scale. So as this oxygen was being released by the cyanobacteria, iron was being deposited on the seafloor in the deeper parts of the oceans. So we accumulate these huge amounts of iron, and they soaked up the oxygen. But eventually the iron got consumed. The iron resource in the ocean was completely consumed, and all the iron got oxidized. And from then on, oxygen began to leak into the atmosphere. So these little slimy bugs that made these stromatolites that you see here in this sample, these slimy bugs changed the atmosphere forever, and they made it possible for more advanced organisms like ourselves to survive. But that was actually a global environmental crisis, the Earth's first major pollution crisis, because you must remember that at that time oxygen was actually a waste product. It was a waste material. And most of the organisms that were alive at the same time as these were anaerobic. For them, oxygen was a poison. So this was a major crisis in Earth history, and it wiped out the majority of life forms living at that time, or coexisting with these bacteria, these cyanobacteria at that time. But of course for us it was good news, because from their disaster, you know, we became possible. So it's a very interesting story. So the oxygen atmosphere then began to gradually increase, and by 2,000 million years ago, there was enough oxygen in the atmosphere to produce these kinds of rocks. And from then on, it just went up and up and up and up, and finally now it's 21%.
And so, based on scientific evidence available, today's atmosphere, known as the modern atmosphere, came about. Land-based life was formed, and our planet was colonized by plants, very different from the other planets, Venus and Mars. But I want you to consider the atmospheres of these two planets very carefully for your task today. Have a careful look at the data presented in this table. It compares Venus, Mars, and Earth according to atmospheric composition, temperature, and size. Using this data, as well as the information you have accumulated during this lesson, write a report on why you think the atmospheres of Venus and Mars have the composition and appearance they do today. You may also choose to do some additional research about these planets before completing the task. I will see you in our next lesson, where we will investigate the way in which our atmosphere interacts with the sun.